So hello everyone, this is the last session that we have for the day, and we will start with Christian Flindt on dynamic quantum transport in mesoscopic conductors.
All right, so thanks, Mr. Chairman, and let me first thank the organizers, Anton and Florian, for putting together this workshop. I think it's a great idea, so thanks for doing it. And also, thanks for the invitation to come here and tell you about some of the work that we've been doing over the last few years. So the title of my talk is Dynamic Quantum Transport in Mesoscopic Conductors. That's quite a broad title, but I chose that because I also wanted to start by first introducing you to this field of research before discussing in more detail some of the things we've been doing. So several people have been involved in the work, and I don't mention all of them here on the first slide, but I do want to point out Menmoy Saha, who is a PhD student in her second year in the group, and also Pedro Portugal, who is a postdoc in the group, and both of them have been heavily involved in the projects that I'll talk about. Okay, so the outline of the next 30 minutes or so, as I mentioned, I'll start by giving you an introduction to dynamic quantum transport, what this field about, and talk a bit about what has happened in the past. And then once we've done that, then I'll move on to talk about two projects that we've been working on the last 1 or 2 years. First, I'll tell you about what we call negative interference currents, and I'll come back to explain to you what that is. And then after that, I'll move on to talk about heat pulses in mesoscopic conductors. And then I'll conclude by conclusions and also perhaps look a bit at some questions we might think about in the future. So there are two works here that I'll try to cover, two short papers that came out this year and last year. All right, so let's start with dynamic quantum transport. So the typical systems that we have in mind are these types of two-terminal setups. So you have some central scatterer, you have left and right electrodes, so reservoirs with electrons in, that are connected by some leads into this mesoscopic sample there. Now the following you can apply, for example, a voltage bias across your system, and you can drive a current of electrons from the left reservoir onto the sample, where it's either is transmitted through to the right reservoir, where it generates a current, or the electrons are reflected back to the left reservoir. So we work at low temperatures, typically say 100 milli-K, so that quantum effects become important. And also these systems are typically quite small, so they're smaller than the coherence length of the electrons. So the whole quantum transport process here is a fully quantum mechanical problem where electrons can interfere and so forth as they propagate through the device. Now, theoretically, we can describe the transport with these Landauer-Büttiger formulas here. Let me stress at this point here, I'm not yet talking about dynamic transport. This is stationary, so we have fixed voltages or we have fixed temperature differences, and then we can write down these perhaps well-known Landauer-Büttiger formulas. So the electric current is just given by the difference of the Fermi functions in the two reservoirs, where you can have different temperatures and chemical potentials. Then we have a transmission probability for an electron to come in with a certain energy E and being transmitted through the device. And then finally, we have to sum over the conduction channels that we have in the problem and integrate over the energy. Then we get the electric current. And you can write similar expression for the heat current. That's what I show you down here. All right, so we can look at a very simple example first. If we assume that we just have a single conduction channel that is fully transmitting, so the transmission probability is just 1, then you can easily carry out these integrals, and then you find that the electric current is just E squared over H, so the conductance quantum times the voltage. Similarly, you can calculate the heat current. It's a bit more complicated, but not too bad. You get this expression here with Boltzmann's constant, Planck's constant, and then temperature squared on one side minus temperature squared on the other side. So in this case, it's a nonlinear function of the temperatures. But of course, if you have a little delta T, a small temperature gradient, then we can linearize this expression around the base temperature, and then we also get this kind of linear response expression here, where we also have now a thermal conductance quantum given by Boltzmann's constant, Planck's constant, and in this case also the temperature. So the upshot here is that the conductance, both the electric and the thermal conductance here, is quantized. You get one quantum of conductance per conduction channel. So this is kind of a fundamental prediction based on this Landauer-Büttiger formalism, but it's also been verified experimentally. So the quantization of the electric conductance was done back in the 80s, some experiments in Delft and some in Cambridge. And they had this kind of structure here, a two-dimensional electron gas with a split gate on top. So you have a narrow constriction here, whose width you can control with a back gate. So you can apply a very negative back gate and completely pinch off the contact there. But then you can also slowly increase the gate voltage there, and then you, one after another, open up conduction channels, and you see there indeed the conductance there jumps in units of G0, or perhaps 2 G0 if you also include the spin degree of freedom, right? So this was back in the 80s that one saw this quantization of the electric conductance, and then it took another 25 years before people then also measured the corresponding thermal conductance for these kind of electronic conductors. This was done in 2013 in the group of Frédéric Pierre in Paris. Had a bit more complicated setup, but still they had a conductor there where they could control the number of conduction channels. They could apply temperature difference across it. And then, as you see over on the right-hand side, they plot this thermal conductivity as a function of the number of open channels. And you see indeed that there's a linear dependence there. So this was back in 2013. And of course, at this point here again, I've only looked at stationary transport, right? So either fixed voltage or fixed temperature difference. So it's not yet dynamic. But of course, you can also start to think about a dynamic drive, where we have a time dependence, for example, in our voltage. And there's also been experiments on that. I'd like to point out a very nice experiment here from Christian Gladley's group in Paris, 2013. And again, they had one of these quantum pond contacts, but now as you can see, they applied a time-dependent voltage. So they had a voltage they could modulate in time, here I think in a gigahertz regime. And now the point is you can apply a voltage, and when you do that, you generate some complicated mix of electrons and holes, and you generate a lump of charge that can move towards your quantum pond contact, where again it can be transmitted or reflected. And now again, they had a single channel here. And of course, in this situation here, the number of electrons and holes that you excite depends crucially on the shape of your voltage pulse. So depending on what kind of voltage pulse you will get a different number of electrons and holes in a pulse. And you may not know that a priori. But if you look at the average current, you can convince yourself that it can be written in this simple form here. You just have the transmission of your quantum pond contact, the charge of the electron, the frequency of the drive, and then it's simply the number of electrons minus the number of holes, right? They contribute with opposite signs in your current. So if you measure the current, you can see at least what's the, say, surplus of electrons or surplus of holes in your pulse, right? But you don't know the exact numbers in E or in H separately. But if you also want to do those, or have access to them, then you can measure the low-frequency noise. So the zero-frequency current correlation function, which then takes the form that I write there, so S. And it's given by a few different terms. There's this d times 1 minus d. That's the random partitioning noise. And a charge comes in, either it's reflected or transmitted or reflected. Then you have E squared. That's because it's a current correlation function, so charge squared. You have the frequency. And now in this case here, you get the number of electrons plus the number of holes. And it's simply because if you have an incoming charge that's randomly reflected, well, then the randomness that's generated by the electron is the same that you generate for a hole. So unlike the current, where they have opposite signs because of the opposite charge, then in the noise, they add up together, so you have Ne plus NH. And then, of course, if you measure those two quantities, then you can deduce, okay, how many electrons and how many holes did I have in my pulse. And that's basically what they looked at here in this experiment. They tried to apply different types of pulses, and then from the current and the noise, they could deduce, okay, how many charges, electrons, and holes did we have in the pulse. And now the key point of the experiment here was that they wanted to confirm an old prediction by Levitov and co-workers from the 90s. They basically looked into this problem and asked themselves, is it possible to apply a time-dependent pulse in such a way that you only generate one electron but zero holes, right? So Levitov and co-workers, they analyzed this problem and they realized, yes, it is possible, but only if your voltage pulse has the shape of a Lorentzian. All other pulses will generate both electrons and holes, but if you apply a Lorentzian-shaped pulse with the right amplitude, then you will generate just one single electron that can then go into your conductor, right? So you have your electron that flies on top of the Fermi sea, and now this is the closest we could come to a photon in quantum optics, right? And this has then led to the whole field that's now called electron quantum optics, where people try to do quantum optics experiments, but now on chip with electrons on top of the Fermi sea. So they managed to do this, and they could show that they could generate these levitons here. Let me just then point out here, of course, people often are confused. Say, if only one electron is created, I mean, there must be a hole somewhere else, right? Because the number of fermions is, of course, preserved. And indeed, that is what happens. If you analyze this carefully, you will see that where the voltage drops, you generate a forward-going electron, but you also generate a hole with opposite momentum that goes the other way. So that goes into your contact, right? So of course, end of the day, there's no electrons coming out of nothing, right? But only one electron going into your scatterer. Okay, so they did this experiment, and of course now you can start to play all kinds of quantum optics games. And I think one very nice thing they did here was they did a Hungermantel experiment that we heard a few times during the conference here. So they applied pulses on both sides and shot levitons onto the quantum point contact at the same time. And you may probably know this Hungermantel experiment from Rochester in the 80s with photons. The idea is you take two sources of photons, shoot them onto a beam splitter, and now if the photons arrive exactly at the same time, then because they're bosons, they will bunch, and they will exit through the same output arm, right? If they arrive at different times, they can go either way. And now they did the same thing here for electrons, and now we have the opposite effect. You have antibunching, because they're fermions, and so when they arrive, they will antibunch and go in opposite direction, and that's a low noise process. So you see here, they applied here pulses on both sides, and there you see the noise. It's a bit of a funny graph because zero noise is at the top, and then increased noise is downwards there, right? And it's plotted as a function of the time delay between the pulses. But you see, if the time delay is zero, the levitons arrive at the same time, and you get this anti-bunching, and you see the suppressed noise there. All right, so this has kind of generated this whole field of electron quantum optics, and it's part of this whole field of dynamic quantum transport. Now, theoretically, we can also calculate these time-dependent currents in these types of systems. We use a generalization of the Landauer-Büttiger formalism. We use something called Fouquet scattering theory. So now suddenly the time-dependent current looks like this. Again, you have the Fermi functions in the two reservoirs, Fl and Fr. Then you have some Fouquet scattering matrices, Jn and Jm, that I define over there. They basically describe the effect of the voltage drive. So when you apply a voltage drive, electrons can get excited or de-excited by interacting with the voltage, and that's what the Jn and Jms describe. And then finally, we have the transmission amplitude of your central scatterer. And compared to the DC case, remember there we had the transmission probability, so amplitude squared. But here actually we have amplitudes at two different energies multiplied together, and this will be important in the following. All right, so I hope I now introduce you to this field of dynamic quantum transport, and I'll then go on to talk about some of the things we have been doing. So the first thing we did recently here is to look at what we call negative interference currents. And in this project here, we looked at some time binding simulations from Xavier Weinzahl's group in Grenoble. So you may know Xavier for his work on this package called T-Quant, which you can use to do simulations of quantum transport in mesoscopic structures. So they looked at this kind of Fabry-Perot interferometer. So then you have two left and right leads connected by a nanowire, and then there are two barriers along the way which kind of function as semi-transparent mirrors in an optical Fabry-Perot cavity. This case is with electrons, and they looked at what happens if you apply a voltage pulse out there on the left. You send electrons into the cavity, and you measure the current in the right electrode. And you see the results over there on the right-hand side. And let's say, at the first glance, it looks quite reasonable. You see a number of peaks in the current, and that simply has to do with how many times electrons bounce back and forth inside the cavity. So you have a first peak that appears if an electron just goes straight through. It's transmitted through the first barrier, the second barrier, it comes out. But of course, the electron could also bounce back and forth once. Then it will be delayed, so you see the second peak there, and there's a third peak and fourth peak, right? So this is pretty much what you would expect from sort of a classical picture. But then what was more interesting and more surprising perhaps was if you look in between the peaks, you suddenly see times where the current turns negative. And you have to remember here, all the time, the voltage is always positive, and you measure the current out in the drain. So there's something funny going on there with these negative currents. You also see there are two different graphs there. Those are for different amplitudes of the voltage. So depending on how big the voltage amplitude is, you sometimes get negative currents, and other times you get positive currents. Okay, so we now wanted to understand this a bit better. So these were numerical simulations, and we wanted to write down a theory for this. So we went back and looked at our Fouquet scattering theory. So again, what we try to do is to calculate the current that I write there at the top, where we have these Fermi functions, the Fouquet scattering matrices Jn and Jm, and then the transmission amplitude of the conductor. In this case, it's a Fabry-Perot interferometer, and then you may know that you can write the total transmission as a sum over all possible paths through the device. Right? Again, you can go straight through, you can go through and bounce back once and twice, and so on. And then the total transmission up in the right corner there, that's a sum over all of these possible transmission paths. So it's a long geometric series there that you have. Okay, but then if we want to evaluate the current, well, we have to look at the transmission amplitude multiplied by itself. And in both cases, you have this long series, and you have to multiply it by itself, right? So we have to try to do that, and this is possible with some patience and hard work. And when you do it, you realize there are two types of terms in this expression here. So we have, again here, if I write all the possible scattering paths there at the top, I have to multiply these amplitudes with itself. And there will, of course, be two types of terms. There will be the ones where I multiply the transmission amplitude for a given path with itself. Right? So there's one here with 0 round trips multiplied by itself with 0 round trips. There's one with 1 round trip times itself, and so forth. So you call those the kind of diagonal terms, right? Then at the same time, we also have all the cross terms where I multiply the amplitude for, say, having 2 round trips inside the cavity times another path which has 5 round trips, right? So there are all these kind of cross terms here. Now one can evaluate these two contributions separately, and then we come down to this rather simple expression at the end, where all these diagonal terms give rise to this expression here. And you just see you have, well, transmission at the first barrier, transmission at the second barrier, and then a certain number of round trips inside, and then a delayed pulse, right? So here, torque theta simply has to do with how many round trips did you take inside. So that's the part that gives rise to these peaks that I already saw you, and this is, let's say, quite easy to understand. You also see that there's no temperature here. So it's kind of, even at high temperatures, you always have this term here. So no surprise here. But now the more interesting part here, that's the one that comes from these crossed terms. And there it is a bit more evolved. We get this expression here, where the first part there, R1, R2, that has to do with bouncing back and forth here. And L, that's the difference in the number of round trips for two different paths. So that has to do with the interferometer itself. Then we have a chi function there, which is defined here, which is a ratio of two time scales. One of them has to do with how long time you spend inside the cavity, and then we divide by tau beta, which is a thermal time scale that's defined here. And that basically has to do with how long time can you propagate until you lose your interference. So it tells you how long can you stay coherent. So that's determined by this tau beta, and you can see if temperature is 0, well, you can go on forever. But as you crank up the temperature, this time scale becomes shorter and shorter. And as a result, this chi function here, if you take the 0 temperature, it's basically equal to 1, and we have that full term there. And then if you increase the temperature, the time scale goes to 0, and the chi function goes to 0, and you kill that whole sum there. So clearly, the sum is only there at low temperatures. And then finally, we take the real part of something we call the excess correlation function. I won't go into much detail about what that is, but it's basically a function that encodes the information about the voltage pulse. So with this, we basically have a theory for these currents that we saw. And of course, now we can compare to what they saw in their numerics. So here to the left, we have the Xavier-Weinthals numerical calculations, and there on the right-hand side, we have our theoretical prediction. And you see we get very good agreement. We get the central peaks there, and indeed we also have these regions where the current turns negative. And it's really due to this second part here, which again is an interference effect between different scattering paths through your cavity. So you can also see we have for two different amplitudes of the voltage, that this Q factor here, you can see again, sometimes it's positive, sometimes it's negative, and it's of course because the amplitude of the voltage goes into this exponential there, and we take the real part, so that gives you an oscillatory behavior. And then finally, up in the corner there, you see results for different temperatures. Blue is cold and red is hot, and you can see indeed as we increase the temperature, well, this negative interference current goes away. So it's clearly a quantum mechanical effect that we only have at low temperatures. Okay, so these were simulations that Weinthal did for Gaussian pulses. It turns out it's quite hard to simulate these Lorentzian pulses because they have long tails. But in theory, in our calculations, then we can just put in Lorentzian pulses, so that's what we see here. Again, you see the same phenomena. depending on the height of the pulse, we get either positive or negative currents here you see to the left. And to the right, we see that it's clearly an AC effect, because if we make the pulses wider and wider, they come closer to a DC current. And you can see there that blue is a narrow pulse, you get the negative currents. But when we go up to the green one, where we have wide pulses, then this effect goes away. So the pulses have to be narrow compared to the size of the cavity. Anyway, so we think we have an explanation for this phenomenon. It's due to this interference between different scattering paths. And of course, so what do we do next? Well, now we're waiting and hoping for experiments. And I know that Christoph Beuerle in Grenoble, this year he got an advanced ERC grant to do this type of experiment. And one of the things he's setting out for is to measure these negative currents. So we're now, of course, crossing fingers that they can see them. It's probably a difficult experiment, but fingers crossed. All right, so that concluded the first part here on the negative interference currents. And I'll now move on to this next part on heat pulses in mesoscopic conductors. And I should say, if the first part perhaps can be measured in a year or two, then here we are moving into a bit more science fiction. So this is perhaps something out in the future. But of course, as theoreticians, we can always think and think about what we might see in the future. All right, so heat pulses in mesoscopic conductors, what's the idea? Well, so far, we looked at time-dependent voltages, and we can just go back and see how can we actually understand them. Well, if I now look at my left reservoir and think about just as isolated, so before I couple it to anything, then I can describe it with a thermal density matrix. There's a temperature T0, there's a chemical potential mu0. And now if I do a voltage pulse, what I do is in my Hamiltonian, I take my initial Hamiltonian of the electrons there, and then I add a voltage which couples to the charge, so Q, right? So I put in this voltage term here, and then now I can apply a time-dependent voltage. And now I can ask, so what actually happens to my density matrix if I evolve with this Hamiltonian here? I can do that over here. I just plug in time evolution operators on each side and let things evolve. Now what I realize is that, well, the Hamiltonian itself preserves particles, so H0 and N commute. But also the density matrix is just given by H0 and N. So actually everything here commutes. So my evolution operator U here can just be pulled through and it eats the new dagger. And I see that at the end of the day, my time-evolved density matrix is actually the same as the initial density matrix. So at first you think, okay, actually nothing happens. I do these voltage pulses, but nothing happens. But it's not quite true, because of course I've changed my Hamiltonian. So the Hamiltonian has changed, although the density matrix hasn't changed. Right, so I have a new Hamiltonian. And now at the later time row of t, of course I don't want to write that in terms of the old Hamiltonian. I want to write it at the Hamiltonian at time t. But I can just replace H0 by H of t minus the voltage, plug it into my density matrix, and now I get a new thermal density matrix, right? It's exactly the same before. I've just written now in terms of H of t. And now you see in this kind of expression, what happens is that then the chemical potential changes. I get the original chemical potential, but times the voltage. Okay, that should not be a surprise, right? I simply change my voltage, that will change the chemical potential. Okay, good. So if you buy this one, then I'll say, okay, now I'm going to do something more. I'm going to add something more in my Hamiltonian. I'm going to add a term like this, W of t, that's some driving field that I want to control. And it's coupled now to the total energy of the system, measured with respect to the chemical potential of the reservoir. And now the same exercise can be done. Again, I see that everything commutes, so the density matrix doesn't change. But I can again say, well, even though it hasn't changed, I have changed my Hamiltonian. And now I want to plug in my new H of t in my density matrix. I can do that. And lo and behold, I again have a thermal density matrix. Again, the chemical potential changed, but now the temperature has also changed. So now the temperature is T0 plus W of t times T0. So actually, by implementing this Hamiltonian here, I change the temperature. Okay, how should you think about this? Well, I like you to think about how an engine works. So you know, if you have a cylinder with a gas in, you have a piston, well, then you can push in the piston, then you reduce the volume of the gas, you do work, you do PV work right against the pressure. If you do it fast, there's no time for heat to escape, there's no entropy production. So all the work that you do, it goes to increasing the energy of the gas, and the temperature goes up. Right, so that's how it works in an engine. And of course, since there's no entropy production, it's a reversible process. So I can pull out the piston again, and the temperature goes down again, right? So having a piston where I do work on a gas, I can use that to change the temperature. And that's in essence what this Hamiltonian describes, how we do work on the system in such a way that the temperature changes. And I should mention that there are some other people who also looked into this. Even there's a paper back from Lottinger where he used it not to describe time-dependent temperatures, but he had some, let's say he looked at a case where there's a fixed temperature. All right, so based on this, we've built a Fouquet scattering matrix. So J here, that was the Fouquet scattering matrix describing a voltage pulse. And we now, after a lot of hard work, Pedro, he worked with for almost 2 years to find out what's the corresponding Fouquet scattering matrix describing these temperature changes. It looks innocent and simple, but it was in fact a very difficult task to get this right. So this is our Fouquet scattering matrix for these temperature or heat pulses. And of course, now we can put them into our machinery. We can calculate electric currents and heat currents and so forth. Oops. So we've done that, and one check is if you do these pulses very, very slowly, right, very, very slow frequency, there can only be one result that must come out. That's what I write up there, t squared minus t squared, right? That's what we had in the DC case. We check temperature squared here, minus temperature squared here. If I now slowly change my temperature, it must just be the same result, but just for the time-dependent temperature inserted, it has to be that. So it must give this result if I do it slowly, and that's what we check over on the right-hand side, the red graph there, or the red line. That's what we get out of our full Fouquet scattering theory. We get that out for, I think, a Lorentzian pulse. And now the dashed line, that is this adiabatic assumption. So you see it fits very well. It's exactly how it should be. Any theory for this kind of pulses here must fulfill this criteria. We also see with the blue line, that's the corresponding electric current, and it's identically 0. And that has to do with the fact that when we drive these pulses here, you excite, that kind of electron hole symmetry, so you excite the equal amount of electrons and holes. So they're charge-neutral pulses. They don't carry any no electric current. It's just electrons and holes going together. All right, so that's one important checkpoint of our theory. Another one has to do with if we go to low amplitudes. So just let me say here, what I did first here was I looked at the case where the drive is slow, so low frequencies, but arbitrary amplitude. We saw that we get this adiabatic result. And then the other important check I can do is I can say, well, what if we have a very low amplitude, but arbitrary driving frequency? What happens in that case is that then we go into the linear response regime, because we have a very little driving amplitude, and then we expect the fluctuation dissipation theorem to hold. And you may know that from electric transport, that there's a relation like this between the left-hand side, the equilibrium noise power of your electric current, and then on the right-hand side, the electric conductance at a finite frequency. So this certainly holds for electric currents, and what we show here, you also get it for heat currents. This has in fact been debated in the past, whether is there really a fluctuation dissipation theorem for heat currents, and here we show, yeah, there is. But the important thing is, and that's what we get out of our theory, when you calculate the finite frequency thermal conductance, there's a high frequency quantum correction, so you get this red h bar omega squared that kicks in at high frequencies. If you don't have that, you won't get the fluctuation dissipation theorem, but in our theory, we get it out correctly, and then things fall into place. So we have, say, 2 important checkpoints of the theory. We've checked that it works at slow drives and arbitrary amplitudes, and at arbitrary frequencies, but slow amplitudes. And of course, once we've checked that, that's important checkpoints. And now we hope that it also works when we go into this kind of uncharted territory where neither the frequency or the amplitude is small. So for this, we've done many different calculations. I won't show all of them, but I think one nice result that I was quite curious about myself is indeed, what now if we do a Hungo-Mandel experiment with heat pulses? So you apply a heat pulse to the left and to the right, you send them onto the quantum point contact, what will happen? And again, it took a long time for us to get this theory here. So for a long time I could go, and 1 week I was thinking, well, it's electrons and holes, they don't have a charge, they carry heat, sounds like a boson. So I thought, okay, that's a bosonic excitation. Then next week I thought, well, but they are made of electrons and holes, which are fermions, so they cannot forget that they were fermions. So then that week I thought, okay, it's fermions. So then the following week I thought, no, but they must be boson, right? Back and forth, and of course, in the end of the day, you have to do the calculations, so that's what I'll show you in a moment. If we send 2 heat pulses onto each side of the quantum point contact, what then happens? That's what we see here. You get a strong suppression of the noise there when they hit the quantum point contact at the same time, and that is a fermionic signature. So at this point here, it looks like these heat pulses, they antibunch, and as such, they should be fermions. All right, so that pretty much brings me to the end. I mean, so I told you about this field of dynamic quantum transport, and we saw these negative currents, and I told you about heat pulses in mesoscopic conductors. Of course, now there are many open questions, so I'll just finish with a slide with some of the things we are wondering about. So of course, in terms of these negative interference currents, well, first of all, I think at this point here, the best thing we can do is to wait for the experiments, because they might happen this year or next year. And let's say before we can do something, I think they've done the experiments. Whether we will see these negative currents or not, I'm not so sure yet. But this will be interesting to see. Can they see it in an experiment, right? But certainly it would be interesting to understand what's the role of interactions here, because we used a non-interacting theory. So we don't see effects of interactions, and it would be kind of interesting to know what now if actually electrons interact inside the cavity. How will that affect these currents? That's still an open question there. Then another important question related to the heat pulses, how can we generate them? I wrote sort of a general formal Hamiltonian with some field coupled to the total energy, but how do you actually do that in reality? And that's something we're thinking about now. The point is, in these kind of mesoscopic conductors, we typically work close to the Fermi level, so you have a linear dispersion relation. And basically that means that the energy is basically given by the Fermi velocity times the momentum. So what we basically would need to implement it would be if you somehow could have a time-dependent Fermi velocity. And we think there are some ways where you can somehow wiggle your band structure using some Fouquet engineering. So we have some preliminary results that at least indicate one way that we could generate these heat pulses. Then, of course, the other questions, I told you about these electronic levitons, single particle excitations. Do we have an equivalent for heat? I mean, is there some miraculous pulse that would generate, for example, just a single electron with a single hole that moves together, or some other kind of interesting excitation? There are also questions related to heat pulses and interactions. As I told you, they're charge neutral. There are equally many electrons and holes, but they don't carry charge. How will they then interact? I mean, they probably interact less than normally, so that would be interesting to look at. And then further down the road, you can start to think, okay, if we can somehow understand the interactions, can we also start to entangle these heat pulses, right? And what happens now, if you think about it in thermodynamics, if I have some heat here that's entangled with some heat here, what's the laws of thermodynamics? I mean, this we have to see, right? All right, so with that, I'd like to thank you for your attention.
Thank you. Thank you, Christian, for this very nice talk, very inspiring. Any questions in the audience? Then I will start with a question, because you have this analogy a bit with quantum optics that is quite clear there. And you have then the dispersion relation of your electron is quadratic, I suppose, with the k vector.
It's linear.
It's linear.
Yeah, because we do have parabolic, right? But then we work close to the Fermi level, and there you linearize it.
Okay.
So it is linear, yeah.
And it wouldn't change if you use, for example, graphene, for example?
Actually, people are now doing, there are two recent science papers where people did levitons in graphene.
Yeah.
Yeah, they do. I mean, they do see some differences. It's actually something I kind of would like to look into, because of course suddenly you have perhaps some extra channels and so on. So it changes something.
And for the levitons and the heat levitons, so when it propagates contrary to a photon, when it's propagating vacuum, it doesn't interact with anything. But there you have this fermionic nature. They will interact with the environment, I suppose. What would be the main channel of decoherence?
Yeah, that's a good question. I mean, people have also looked at this decoherence question for levitons there. And of course, interactions are typically the biggest source. But I mean, often they can travel quite long. So you see many of the effects that you want to see. Because you could of course ask me, how long do they live? What's the phase coherence? And do they collapse at some point? But they travel quite far. And you can do things before.
Even with phonons and due to...
Yeah, it's low temperatures, right? So phonons are typically frozen out, but perhaps interaction
they are frozen
effects.
out, but they can also still, if you excite them, you will also have the deformation potential that could create basically a cloud of phonon.
Yeah, it's possible, yeah.
Okay, any other questions? Yes?
I have a question regarding the first point on this slide, so the negative interference currents. And basically what came to my mind is dissipation. So it looks like that you have a temporal negative current, and you didn't show, at least for the Lorentzian pulses, the kind of long-term evolution. So is there any issue with negative dissipation in there, or is this all fine because it's a dynamic effect?
I think it's all fine. I mean, I don't know if you're thinking about it sort of in terms of like energy conservation and so on.
Yes, exactly.
It's all fine. I mean, the energy is conserved, so there's no problem there.
Thank you.
Okay, let's thank Christian again. Or is there another question? No. Okay, for interest of time, let's move on. Thank you, Christian. Right.